Hello, we are the Reconfigurable Seating System for transit vans, and we represent the articulation portion of this project. Our sponsors are Dr. Joseph Mello and Rich Hollingsworth. My name is Emily.
My name is Anil.
And my name is Rick.
The need for this project stems from seating and storage optimization based on the variable needs of shuttle vans. The solution that our design investigates is a rapidly configurable seating system that allows for additional cargo space or passenger seating based on a need-by-need basis. In the past, previous senior project teams have worked to develop the commercialization and licensing of this patented seating system, and the scope of our team in particular is the seat articulation component design, which refines the motion of this configurable system. Our team went through a very iterative design process, which involved brainstorming, rapid prototyping, and a series of selection matrices in order to narrow down the best ideas. The primary reasons for down selecting to these ideas include the vertical stowed position that maximizes space saved when the seats are pushed together, a simple single user input to deploy the seat, and a system of linkages that allows for a more ergonomic seat back tilt in its deployed state while preserving the perfectly vertical stowed state. Here you can see the progression of our design from PDR, CDR, and finally to our final verification prototype. PDR primarily served as our proof of concept of our design. During CDR, we conducted in-depth and engineering analysis of this design. And lastly, we built a fully functioning seat to verify the manufacturability and functionality of our final design. This final prototype allowed us to conduct testing to verify that we met or didn't meet our specified requirements.
Our final design utilizes two conjoined linkages to simultaneously control the deployment of the seat bottom and the angle of the seat back. This allows for the operation of the seat with a single user input motion. With the addition of the gas spring in the back of the seat, the user simply has to pull a release lever and the seat will stow itself automatically. To deploy the seat, the user simply has to press down on the shoulders of the seat while tilting slightly back and slide it down until the latch is engaged. To verify the functionality of our design, we constructed a prototype out of 1/4-inch aluminum plate, water jet cut into the appropriate components and welded together as necessary. This video of our verification prototype demonstrates the operation and functionality of our design as described previously. To justify our design, there were two primary stages of analysis, the linkage kinematic design and the system structural analysis. To design the linkage, a combination of graphical and analytical methods were utilized to optimize the linkage geometry. This ensured the ergonomics and final geometry of the seat. The tools developed in this process were then expanded to compute forces at all the pin locations for the structural design phase. To ensure our design was sufficiently strong and stiff, we conducted stress analyses on each linkage component modeled as beams, and then followed that up with FEA on critical components.
So I'm going to be talking about the testing performed on the verification prototype. This is necessary to verify a preliminary analysis in a physical environment. We performed a variety of tests, and the ones that I'm going to be talking about are the stiffness, operation effort, and operation time tests. The stiffness test that we performed was designed to measure the amount of deflection under various loading conditions to ensure that the seat does not excessively deflect. We failed to meet our original target specification of 0.25 inches under a vertical loading of 150 pounds. The seat ended up deflecting 0.38 inches, and we will discuss this later when discussing future recommendations. So the operation effort test was designed to measure the force required to articulate the seat from a stowed to a deployed position with the gas spring engaged, and from a deployed to a stowed position with the gas spring disconnected. Based on the gas spring that we implemented in our verification prototype, the gas spring was unfortunately overbalanced, and it required too much effort in order to pass the test. However, we will discuss this later in future recommendations. The final test that we performed was the operation time test, which measured the average time to move from a stowed to a deployed configuration and back to a stowed configuration. This met the requirement of under 5 seconds at an average of 3.6 seconds across test participants. We learned several lessons from the construction of a verification prototype and the testing that occurred on it. The first is that in future iterations of this prototype, we need to improve stiffness. The use of 1/4-inch aluminum is useful for manufacturing, but future design iterations can improve on stiffness by including more cross bracing on the back of the seat near the bottom to reduce transverse deflection. And in addition, improved manufacturing techniques with tighter tolerance can also help. Second is that we need to correctly size the gas spring. We recommend a gas spring with a bleed-off valve instead of a fixed force output be implemented in order to tune the system to exact force requirement of 5 pounds. And in addition, we recommend that the gas spring be correctly sized to length in order to ensure that the seat undergoes the full range of travel. Finally, we hope that future iterations will integrate a locking system into the release latch. This would allow the operator to lock the system in a deployed position. And the nice thing about the system that we used is that it is a modular rotary latching system from Southco, which manufactures release latches that can be locked with a key, which is a possible option and would be easy to replace and integrate. This could also be paired with a component to passively lock the track and latch system as well, if so desired. As a reminder, our team consists of myself, Anil Singh, Emily Sun, and Rick Hall. We would like to thank the university, Cal Poly SLO, and the Mechanical Engineering Department for presenting us with the opportunity to design and create this project. We would also like to thank the Mustang 60 and Aero Hanger machine shops for their time, resources, and expertise in manufacturing this project. Finally, we would like to thank our senior project advisor, Sarah Harding, as well as our project sponsors, Dr. Joseph Mello and Rich Hollinsworth, for their expertise, guidance, and support of this project. Thank you for your time and interest.